The first session this morning is really on the theme of the surface response to plate tectonics, sedimentary response and the vertical response to plate tectonics, and we've got 5 talks coming up on that subject, and we'll aim for an integrated discussion on the subject at the end. But I'm pleased to say our first speaker, our keynote speaker this morning is Nick Christie-Blick, who's visiting us from Lamont, especially for the occasion. And Nick, I think, is going to talk about the tectonic and sedimentary response in the plate tectonic era.
Right, well, thank you very much indeed. This is great to be back at the Geotrack. I can't remember when I was last here. I've been to one of these William Smith deals before, but I can't remember what the topic was. But anyway, it's nice to be back. It must have been good. It must have been excellent, yeah. Okay, so I'm going to have to do this again. Here we go. So my assignment today is, from Rob, is to talk about how stratigraphy has been revolutionized by plate tectonics and how it contributes to understanding tectonic processes. That was what I was told to do. And so I'm going to start off with a little bit of history, context, and then we'll sort of move into some examples. And in particular, I'm going to draw, oops, I'm going to draw upon, oops, it's missing an arrow here. I'm going to draw upon the work I did with Andrew Madoff, and there's an arrow missing there. Work with Andrew Madoff, who is in the bottom right-hand side here, who's a co-author, and the particular example I'm going to draw upon comes from that work. All right, so an anecdote. There are some parts of my slides, by the way, that are not showing up. And we did this on the screen upstairs, but it's not showing up on the screen right here. So a couple of anecdotes, because what it should have said on the previous slide was that I would like to thank Dan McKenzie, who's here in the audience. And there are 2 ways in which I'd like to thank Dan McKenzie. One is this lecture. It was the beach ball lecture that Dan gave at the age of 29 to the assembled first-year students in 1971. And I was there learning about plate tectonics for the first time at Cambridge. And I'd gone to Cambridge to study physics and math. And I was taking some geology on the side and learning about plate tectonics for the first time. And Dan came in as a very excitable, he was even more excitable at 29 than he is now, very excitable person. And he gave this wonderful lecture, which was published in the Geophysical Journal of the Royal Astronomical Society. He gave this wonderful beach ball lecture on the seismicity of the Aegean. And of all the lectures I heard that year, this was the one that registered with me the most. And it wasn't the only reason I wound up not doing physics, but this was certainly amongst them. And then later on, a couple of years later, I was searching around for ideas of what to do for graduate school, and Dan proved to be very helpful. And I was talking to my tutor in this building here, asking him for advice. And he said, look, I'll call up Drummond Matthews. And he got hold of Drummond. He was trying to get hold of Drummond Matthews at Mattingly Rise to get him to give me some advice about where to apply for graduate school. And he was having a lot of trouble getting hold of Drummond Matthews. In this conversation, he said, if I can't get hold of Matthews, I'll call Dan McKenzie. And then after a while, with a bunch of dialing, he finally got through and had a conversation with somebody who I took to be Dan McKenzie. And so on the appointed day, I got on my bicycle. And again, the 2 graphics that are on the bottom of the screen here, the 2 graphics are not coming up at all. So I got on my bicycle to go and see a much younger Dan McKenzie in those days. And I sat down with him for an hour and had a marvelous conversation. And I don't know whether you remember Dan. He said, well, it's Teddy Bullard's birthday. Why don't you come down and have cake? So we went down and we had cake, armed with all this great advice. We went down and had cake. And there was Drummond Matthews looking very nonplussed because he had been waiting around for an hour for this undergraduate who hadn't showed up. And Dan, bless him, had sat down with me and given me all this great advice about going to the United States, which I then took. And Drummond Matthews wondered where I was. Anyway. Okay, so what I'm going to try and do here is talk about some context. And the 2 obvious things about the context are the plate tectonic revolution obviously provided an explanation for the similarities between continents. That was the big thing. And it also challenged the static view of the world, the static view that had gone with the geosynclinal ideas. And also this view that, which I think I probably still learned at Cambridge, the idea that sedimentation somehow alternates with orogenies for no apparent reason, whatever orogenies are. And that stratigraphic elements in close proximity are necessarily related. I mean, they might be, but they were assumed to be. And I've always wondered, why it was. It seems to me that the geological evidence, particularly if you're a southern hemisphere geologist, the geological evidence was pretty profound. I mean, it's one thing to have land bridges to make the tetrapods march from one continent to another, but I don't know quite what you do with the ice sheet. I mean, the ice sheets go out of southern Africa and they come into South America. How did the ice sheets, how were they supposed to cross the Atlantic? I'm not quite sure. I mean, if you knew which way, if you could go to landforms and you could measure the direction of the ice, I'm not sure how you'd ever do that. It's a bit strange, really. But anyway, and I've borrowed the same postage stamp of Alex Tectonic here. So this is a very famous road cut that John Dewey would be familiar with. It's just south of Albany in Catskill. And this is one that generations of students have been misled into the view that sedimentation alternates with orogenies. And so they're told that these steeply dipping turbidites here are steeply dipping because of the Tectonic orogeny, they're told. And then there's an unconformity. And then they're told that the less steeply dipping beds, but still dipping, are part of the Acadian orogeny. The reality, if you look at the geology of New York, is that the deformation was more or less continuous from the mid-Ordovician all the way through to the end of the Devonian. And you can find evidence in the stratigraphy that would support that view. But anyway, this is a famous outcrop where that sort of idea is still promulgated. And I borrowed this from Marshall. This is from Marshall Kay's book. And the idea here, and this is obviously the way in which the static view of the world isn't right, the idea that somehow the geosynclines were somehow more or less in the same place as the Maya geosynclines, and that they weren't far traveled at all, was something that Marshall Kay, who's a predecessor of mine at Columbia, promoted. And I read Bob Dott's wonderful obituary last night about Marshall Kay, because I'd wondered whether Marshall, in the latter years of his life, he died in 1975, he retired in 1970, I wondered whether he had actually got on board. Eldridge this morning at breakfast couldn't recall. In Bob Dott's obituary, he's saying that actually Marshall Kay felt vindicated, because he felt that he had seen the differences between the different settings in which sediments accumulate, and now with plate tectonics he had a way of thinking about what the origins of those different settings might be, but he had recognized that there were differences, and so I'm not quite sure exactly where he stood. I never met the fellow. All right. However, I'd like to draw attention to John Kroll's work, because it's a little bit different. John Kroll's work is in California. California is wonderful because it has active tectonics. So if you're a British geologist, you learned how to map in the Lake District in the Ordovician, and then you're surprised that you can go to the Miocene and find vertical beds. Well, you can do that in California. It's wonderful. But anyway, John Kroll's work, his dissertation was 1947. And what he recognized was that there was a relationship between sediments and faults. I mean, the violin breccia here, this black thing, along the edge of the ridge basin, along the San Gabriel Fault, obviously is recording the sedimentation at the same time as deformation. And not only that, he realized that there had to be big displacements. So at a time when most people like Marshall Kay were thinking about things being basically static, the folks in California, and particularly Kroll, were thinking about large displacements. And in his dissertation, he writes, in writing up the results of my dissertation study, I concluded that no conclusive evidence for the direction and amount of displacement has come to light, but it has to be a big fault because the contrast across the fault is so large. And by the end of the 50s, I raised the hypothesis that linear trends in the basement, the things which look like they're offset, were probably offset laterally by the combined San Gabriel faults and the San Andreas fault by close to 300 kilometers. And so in 1947, he didn't know quite how to measure it because in those days, they were not mapping big enough areas to be able to recognize the offsets, but he recognized that it had to be large. And so that was a very different view from the view that Kay or Stiller had. Okay. All right, so where are we going to go with this? So plate tectonics gives you this new spatial, kinematic, and genetic way of thinking about the world and about what sedimentary basins are, and they have identifiably different character for good reasons, and we can say something about mechanisms for the first time. The other thing is that the qualitative distinctions, like rift basin versus a fallen basin, they were swiftly improved by reference to fault mechanics and geophysical forward models and backstripping in an attempt to get at what the tectonic driving substance was. And an important innovation going along with this in the 1950s, although it didn't become popularized in the academic world until the 80s, was the development of geophysical tools. This was both in the oil industry, but also at places like Lamont. I mean, oceanographic institutions were very much into developing geophysical tools. And this made a huge difference. It made a huge difference in the emergence of plate tectonics, but it also made a huge difference in stratigraphy. Stratigraphy went from being a moribund, very dull field into a very exciting field, and it was the combination of the stratigraphy with the geophysics that did that. And I would say the emergence of seismic stratigraphy in those same years was important, and particularly the recognition of the pervasive discontinuity of sedimentation, which really came out of that. So here's an example of one of Tony Watts's early students, Mike Steckler, his EPSL paper, where they were looking at the substance of the Atlantic margin and trying to get at the tectonic part of it by taking out the compaction and loading of the sediments. So it was the marriage of stratigraphy with geophysics that was very important, and it was an exciting time for that. I would say I arrived at Lamont at the right time in 1983, where it was all kind of exploding. It was great. The other thing with the seismic stratigraphy, which was largely associated with people like Pete Vail and Bob Mitchum, was recognizing the significance of reflection geometry. And I must tell you that being in an oceanographic institution, it took a while for this to sink in. Because when I arrived in 1983, I started teaching this stuff, because I'd been at Exxon. I started teaching this stuff, and what would happen is that the graduate students would take my class and then promptly go back to the marine geology building and go back to doing the tracing booming reflections, which they'd been doing. And it took probably 5 or 10 years for it to kind of sink in at Lamont. But eventually it did. This paper is part of the most recent Atlantic margin work with the IODP drilling. And this is the Rutgers interpretation of the surfaces. I'm not responsible for this. But the philosophy in this is exactly Pete Vail's philosophy. It's the philosophy of using on-lap and off-lap, the terminations or reflections to define the boundaries. And so Pete gets a lot of credit for that. The other thing that happened was that there was a general view that what was driving that was not tectonics, it was sea level change. And it's a view that's very pervasive throughout both academia and industry, and it's almost certainly wrong. This is how you do it properly, in the sense that you take the batch shipping approach and you can use it to get at what the sea level changes are with uncertainties. These are the errors here. This is from Michel Kermentz's work on the basis of that same drilling. The gaps here are the hiatuses associated with sequence boundaries or the unconformities. And you can see that the amplitudes here are in the order of about 25 meters in the early to middle Miocene. This is the famous so-called Hark curve, which has now got almost 8,000 citations. What is most remarkable about the Hark curve, because I was in an office about 3 doors down from Bill Hart when they were doing this work. What was remarkable about it is that this was known to be wrong 3 years before it was published. I mean, I gave a presentation at AGU in 1984 saying this whole methodology doesn't work. And yet this is sort of dominating thinking. And the essence of this is that in all stratigraphy, there is this eustatic signal. And certainly if you go to places which are more simple rather than more complicated, then you can make that sort of argument. But the world is much more complicated in general than that. And I think the eustatic model has gone way too far, and we haven't paid a lot of attention to the other mechanisms, which are of great interest to me. Also, the Bill Hart's amplitudes here, which you can't read, they're about 5 to 10 times these amplitudes. They're completely wrong. Okay, so where are the frontiers, the second half? Where are the frontiers of where we're heading here? At a large scale, the questions have to do with things like how the lithosphere is partitioned, how the extension of the lithosphere is partitioned between the crust as a whole and the top part, the sedimentary basins. And the stratigraphy gives you information about that. And particularly problematic is this whole business of low-angle normal faults, which American geologists don't seem to care about very much, even though they don't have a mechanism. The European geologists seem to be much more open to talking about it. And I'm going to mention just a bit of that, because it's an example of how the sedimentation and the deformation are highly related. And then at a smaller scale, there's a whole business about the origin of sedimentary cyclicity, which, as I say, the general view is that it's sea level doing it all. And the varied role of several different kinds of tectonic processes at different length scales and time scales that might be playing in that. So I'm going to give you an example from the late Cretaceous Fallen Basin, which we picked because it's a time in Earth history where there should be very little used to see, and where you should see a good tectonic signal, so that's why we went to that. And I'm going to mention some work we're trying to get started at the moment in the Gulf of Suez. All right, so here's the example of a hyperextended margin, to use the vernacular. This is Gianretto Manichal's work and all his friends and students and postdocs. And this is a composite cross-section of Western Iberia and Newfoundland put together up here, showing the geometry as they perceive it. Excuse me for banging the microphone again. And on this plot, there are certain corners. These would be the rolling hinges or the convex upward faults, and you can see it both in this diagram here, this cross-section, and also in this cross-section from Donna Whitney's paper of mid-ocean ridges. It turns out that at mid-ocean ridges you get the same features, where there are faults that are flat, which appear to steepen with depth. And they have these hinges. And what's interesting about it is that you would think that this would in fact have resolved all this, and that the flat faults would then be regarded as not being problematical because they were all originally steep faults. They simply flapped over. But in fact, in talking to the people who are actually working on this stuff, I'm getting the impression that that's not resolved as far as they're concerned. I went particularly to all the AGU posters on this last year and had a conversation with every single poster that dealt with this, and it was more or less divided. So the whole business of how you make a flat normal fault is unresolved. Okay, so as some of you know, Mark Anders and I and students have been struggling with this for about 25 years. And so we've looked at a lot of the examples in the Western US, not inconsequential examples, but examples that really made a big difference. And one of them was this example called the Severe Desert Basin, which has a flat fault underneath it dipping at 11 degrees and supposedly with an offset of 47 kilometers. And this is superimposed on Peter DeSelle's very nice balanced cross-section of the severe orogenic belt, the Cretaceous origin that makes the Fallen Basin out here. And the issue here is whether this fault exists at all. And we're on record of saying there's no fault there. That's our solution. There is no fault. This is an unconformity, which you might imagine would change this balanced cross-section quite a lot, because obviously it's a big feature on this cross-section. And it's important for this talk because, of course, it underlies the sedimentary basin. And it was the first one. It was in Brian Wernicke's dissertation, in his first paper, he refers to this example. He compares it with the Mormon Mantis. So it became of interest. And I'm currently agnostic on this. Formally, I'm agnostic because I want to drill a hole in it. But nonetheless, last summer, I got together with this guy called Xiaoping Yuan, who's currently a postdoc in Potsdam. And we decided that we would do something different from what Mark and I had done. Mark and I had said, well, this is impossible. These faults, you can't get the frictional coefficient low enough. And what Xiaoping and I did was to say the opposite, was to take the cross-section that Peter DeSelle's had published, and then to look at that cross-section and to use critical Coulomb wedge theory to get at the frictional coefficient of the thrust faults and the friction coefficient of the extensional faults, both independently, and calculate what they would be. In other words, to make that cross-section of Peters, what would you have to do in order to make the fault work? And so the answer is that it is somewhere between 0.2 and 0.13. That's the static friction. It's not a dynamic friction, it's static friction. That's what you'd have to do. So you then say, well, if I drilled a hole through it, I should get down at 2.8 kilometers. I should find materials that should be consistent with having a friction coefficient of that, if Peter DeSelle's cross-section is correct. So it's a testable hypothesis, right? All right, now what about higher resolution stuff? So this is the second part of the second part. This is part of Andrew Madoff's dissertation. Here's the interior seaway. It's all been folded. There's some broad folds here. There's an area in eastern Utah and western Colorado called the Book Cliffs, which has the most spectacular outcrops of sedimentary rocks. And they come along just in southwestern Colorado. They come along the cliffs here. And Andrew had done a classic study for a master's degree at University of Kansas with Diane Kamola, where he'd come up with a perfectly reasonable interpretation of some measure sections, very nicely done measure sections here. Which when he got to Lamont, we sat down, we were talking about it, and I said, Andrew, this is a real problem because you've got lateral changes in facies which take far too great a distance. They can't be right. I mean, you can't have a change from the shorelines into the offshore that take place over tens of kilometers. That's way too big. is it something to do with the orientation? And there were some other issues. And so we got around this by deciding to redo the entire thing. And one idea was to go into the subsurface. These are all fracking wells, so we had several hundred wells. And then we ran a helicopter along the cliffs and took a panorama of pictures. So all the things you couldn't quite see with your binoculars, we resolved. And it made a huge difference. It totally changed the interpretation. It made it much messier, but it made it much more interesting. So this doesn't look right. The paper is mostly ignored because it looks too complicated. What you can see here is a bunch of cycles that originally Andrew had going this way, that actually come this way. And the inclination here looks steep. The inclination is actually about half the gradient of the New Jersey shelf. I mean, it's a very, very low gradient. And the angles are so small, the only way to see them is with this panorama. You can see them with a helicopter flight. You can't see them from the ground with the binoculars, but if you get the panorama looking straight at the cliff, you can see them. So that's where the geometry comes from. The time span here is 2.1 million, no more than 2.1 million years, and it's probably closer to about 1 million or 1.5 million. So very, very high resolution. And so we've taken it apart. It started off as being 2 cycles. It's now got 6 cycles, only 5 of which are in the outcrop. There are some incised valleys at the top. This changed a lot. These are all shoreline deposits. They are shoaling upward units that have hummocky cross-stratification. I thought I'd better put a picture in for the geophysicists. This is what it looks like in the beaches there. And here's a simplified diagram of how it's all put together with some funny arrangement, because this goes over the top of these 2 and this comes over the top of these. But this is then clearly documented by the data. And we made a bunch of maps. So this is now thickness maps of each cycle. I'm just showing one here for the first parasequence. It's thick here and it pinches out, so you can make maps. And this is an example of a well log cross-section where you can get the geometry in the well logs using the gamma ray and the resistivity logs. And then you can map them all out. So this is the rollover for one. This is the rollover for the next. And you can see that the orientation changes to over here. And that's because what's happening is that the basin is actually tilting and untilting at a length scale of a few tens of kilometers. So you're in a fallen basin which is flexing down towards the origin, but in detail, at a time scale of hundreds of thousands of years, the basin is actually doing this. So there has to be some brittle deformation in the fall at depth, which is causing the stratigraphy to do this. And you can record it all in the sediments, and that's what the data are showing here. So the origin of the cyclicity in these sediments has nothing whatever to do with sea level change. It has entirely to do with the deflections at a small scale inside the fallen basin. That's the point of it. So here's the very much more pleasing original interpretation in Andrew's master's thesis. Here's where it went. This is much more publishable, because it looks like an Exxon cross-section should look. This is the reality. And this was a comparison we did with Ken Miller's sea level curve and also the timing of thrusting. And it turns out that you know, if you compare it with Ken's curve, and I'm not sure how good the sea level curve is in the Cretaceous, you could argue about that, there seems to be no relationship at all between the cyclicity that Andrew's got, and very well calibrated using ammonites and ash beds, very well calibrated in terms of timing. It doesn't work at all. Okay, I've got 2 more minutes here, and I want to talk to you about an example which we're trying to get going. And there's a graduate student at the University of Cairo, and my colleague Ahmed El-Bakouki at University of Cairo. And I've been trying to get an Egyptian student to Lamont. It turns out to be very hard because they don't have good enough English to pass muster with admissions. But they're actually very interesting. And Raed Badr is actually one of their best students. And so the compromise I came up with was to have him do the work at the University of Cairo. And the idea of that was that it's very hard to persuade NSF that an American student should be out in the field in the desert in Egypt, because there's this view that maybe this is dangerous. And so if you have an Egyptian student working in the desert, there's no problem at all. So this is some very nice work by Ian Sharp, published in 2000. And the idea is to extend Ian Sharp's work. What you can see here is lots of geometry. There are beautiful faults. These are fault propagation folds associated with extension. So the early extension, as the fault propagates up, you see it in the North Sea too, you get this folding going on, and the folding is taking place as the stratigraphy is being deposited. So what you have the opportunity in the early Miocene in the Gulf of Suez to see cyclicity that is both tectonic and eustatic. We know what the early Miocene eustatic signal is. Now the question is, how is it partitioned? How does the deformation relate to the cyclicity? How does the sea level change relate to the cyclicity when you have them both in the same place? And I'm going to show you a little detail of that panel. So here we are. There's 101% outcrop. Isn't that magnificent? So here's the detail. There's a conglomerate bed there and here, and you can see them on the Ian's cross-section here. And also you can see some very nice truncation there, and you can see some very nice downlap there. In other words, there's geometry that you can map out in the field. And the idea here is to calibrate all of the stratigraphy using strontium isotopes. There are shell beds about every 2 or 3 meters. So you calibrate, you get the timing out of the shell beds. There are also in the marls, the marine marls, there are lots of microfossils, and we've got some samples of the forams already. So the idea is to use the microfossils and the macrofossils to get the timing of the growth of these structures at very, very high resolution. So you can do the high resolution in the outcrop, and then you can date it to high resolution and answer questions that in the past we would not have been able to answer. You're looking at the same kind of thing that Andrew did in the book Cliffs, but now you're also trying to calibrate it. So that's all very exciting. If we can pull it off, and who knows. So wrapping things up here, plate tectonics gave a new way of thinking about the Earth's sedimentary record, and it happened at about the right time, and it became very exciting. It was the integration with geophysics, I think, was very important. That started about the time I graduated with a PhD. Certainly by the time I got to Lamont, lots of ways in which this was put together. And I would say the frontiers today are in part on the big scale phenomena like the whole issue of detachment faults, and then also at very high spatial and temporal resolution. There's some really interesting questions that are quite different from the big scale things, but where you can actually get a phenomena at very high resolution. And I think that's where some of the future is. So, thank you very much indeed.
Right, thank you very much, Nick. Nick has kept beautifully to time there, so we've got plenty of time for questions. Jonathan is bursting to leap out of his chair.
All right, okay. You've got 4 minutes, guys.
Jonathan Turner from Radioactive Waste Management. Yeah. Isn't part of the answer to your super low friction coefficients that the low angle normal faults require to introduce the influence of high pore pressures?
Yeah, so, is this on? Can you hear me? Yeah. Okay, so there are lots of different examples. The problem with the low angle fault community is that there's a tendency to sort of view them all as being the same thing. And there are lots of different examples. There are certainly places, I would say the Alta Tiberina fault in Italy would be an example of a place where high fluid pressure, in that case CO2, likely is playing, if it is a low angle fault, is likely playing an important role. It's not clear in a place like Severe Desert where the Paleozoic was fully lithified that there's high pore pressure there. I mean, I would pose it as being something you would go measure. If you drill a hole, you want to measure it. There's no evidence in the holes that have been drilled that it's elevated. So I would say it may be part of the solution in some examples, but not necessarily. I think every example we've looked at has been different. Every example has had its own issues. Yeah.
Anybody else? Lydia. Can I just remind questioners at the obvious point of mention their name for those not in the room, but for those in the computer.
Lydia Lonergan at Imperial College. Would you think that one of the other frontiers is actually thinking about sediment routing systems, so thinking about some of this stuff in 3 dimensions, where the sediments are coming from, where they're going, what the effect of sediment supply is and all of these things, because that's what a lot of people are involved in at the moment. And that links back to plate tectonics, or at least to tectonics in terms of vertical movements, as people were talking about yesterday, for example, Nicky White.
Yeah, I'm sort of torn on that. I mean, I understand the rationale for doing that. And you know, when it was like a big deal in the United States, the source to sink days, I mean, I went to several of those meetings. And at the end of those meetings, I was never quite satisfied, because I would sit down with Chuck Nitra and I'd say, Chuck, you know, supposing you measure the flux as being X. Now suppose it's not X, it's 2X, or it's half X. What difference does it make? So the question is, in understanding, you know, the flux of sediments, does it really matter? What bigger issue are you tackling by putting numbers on it? And I understand that there is a lot of interest in trying to see things at that level. I'm struggling myself with understanding what the most interesting thing to come out of that would be.
critically affects your stratigraphic relationships, though. I mean, that's one obvious.
Stratigraphic relationships are things which you can observe all by themselves. You don't need to know about
the
fluxes.
The explanation of what they might be is related to that feature.
Yeah.
Tony showed how many years ago? 30?
They're amongst the they're definitely amongst the variables. Yeah, they're definitely amongst the variables. We've got 1 minute here.
Eldridge Morse, University of California, Davis. Thanks, Nick, for a very interesting paper. It's nice to hear something about what's going on these days in low-angle normal faults. I have a kind of a soft spot in my heart for these things because I mapped one of the first ones ever, I think, described back in the early 60s when before I went on to ophiolites, and we actually found also low-angle normal faults in the Teunis complex. So it's nice to hear some progress. Thank you.
Yeah, the issue with the low, I would say the number one issue with the low-angle normal faults is not whether they're low-angle, it's what they were doing when they were active. Because most of them are tilted higher-angle faults. Some of them are these rolling hinges. We have not yet found a good example of a rolling hinge in the continents. The ones in the mid-ocean ridges are brilliant. And I think the ones at the hyperextended margins are pretty good too. But it's remarkable that in places like the Basin Range, where you expect to find them, we're having a devil of a time finding them. The Black Mountains along the flank of Death Valley, which was one of the key examples, turns out not to be a rolling hinge.
Take one more, and then one more.
Hank Frankel, University of Missouri, Kansas City. In honor of Bob Dott, who would like me to make sure you know this, I guess. Marshall Kay did become a mobilist in 1975, along with Jim Colbert in their book on geology.
Okay, fine. I appreciate it, yeah.
Okay, thank you very much. Yeah. Okay, and our next speaker is Paul Green, who is possibly our most far-travelled speaker because he's joining us from Melbourne today. Most of the conference so far, with some exceptions, has been about things moving horizontally. Paul is going to talk to us about things moving anomalously vertically, I believe.
Well, I hope it's not too anomalous. But what I am going to do, in contrast to everyone else, is talk about rocks that aren't there anymore. And that needs a bit of a shift in emphasis. So, and I must try not to touch the black button. This is my basic message. So I start at the beginning. So I put this at the beginning so that I can get it out to you. And basically, what we've been studying for the last 30 years is these vertical movements in non-tectonic areas like Pacific continental margins and cratonic interiors, where we're seeing kilometre scale section deposited and then removed in a number of separate episodes with a time scale of tens of millions of years. These are things that can't be explained as far as I know, although maybe some people have a different idea. But the fact is that they leave very little trace. These episodes of deposition leave very little trace because almost everything's removed again. That causes quite a lot of controversy because a lot of geologists aren't really willing to believe in this sort of phantom geology. But what I'm trying to explain today is that it's real, it happens, we need to explain it. And if we can explain it, then we might find something more out about the way the Earth works and plate tectonics. I don't want to talk too much about this, but just to emphasise really, that we take a multidisciplinary approach to this. We combine evidence from paleothermal, paleoburial indicators, which are often the only way of detecting these episodes. We combine that with landscape analysis, looking at cross-cutting relationships between different erosion surfaces to build up a relative denudation chronology, but in recognising that the reason we see these surfaces today is that they've been preserved by burial and then exposed at a later date, and I'll come back to that later. And of course we integrate that with geology, and you might think that's obvious, but as I'll show you, it's not obvious to everyone. So beginning with a case study from Namibia here, I'm going to try not to use that. On the left there's a map of Namibia showing these localities in the northwest of Namibia. In particular, these late Carboniferous, early Permian landscapes are being exhumed today and revealed, and they've been preserved by burial since that time. You can see this beautiful U-shaped valley that we drove through when we were there, and it could be in the Lake District. It's just a beautiful U-shaped valley. You could be anywhere that's glaciated, really. And the lower left there's a picture showing roche-moutonné in basement, beautifully created roche-moutonné, and it's buried by the Dwicker Tillite there. And above the Dwicker Tillite, there's the Etendeka volcanics, early Cretaceous Etendeka volcanics. And so I will use this. The geology here tells us that we've got this basement. It was exhumed to the surface in Dwicker time, and then there's an unconformity here, and then it came back to the surface in the early Cretaceous when the volcanics were deposited on top. The thermochronology, basically after data in this basement rock here, defines a series of cooling episodes. The sample from this rock defines cooling below 110 degrees in the 200 to 180 MA window, and then we see another cooling episode here at about 100 MA and another one here. So if we combine the constraints that we get from after with the geological constraints that this basement section was near the surface at that time, and we also include in that the fact that this regional basement was exhumed in the late Carboniferous to the surface, we find this history of exhumation, burial, maybe another phase in there, and final exhumation to the surface. Here's another example, very similar. This is from the work by Becky Flowers and Sherry Kelly in this borehole in Kansas, where the borehole is located here. We've got granite basement here overlain by Cambrian, Permian and Cretaceous sandstone, and their low temperature thermochronology data, they define 3 cooling episodes here. And again, the geology tells us that this basement was at the surface in the Cambrian, very close to the surface in the Permian, very close to the surface in the Cretaceous. So again, we have this burial, exhumation, burial, exhumation, burial. I could show you a large number of examples like that, but they all show more or less the same time, this deposition, erosion, deposition, erosion. And you can see these erosional episodes leave very little evidence that they ever took place and that this section was ever deposited. You've got a little bit of remnant Cambrian here, a little bit of remnant Permian, a little bit of Cretaceous. And it wouldn't take too much more erosion to have removed all that, and then you would have removed the evidence for this episodic history. So it's where we get these sedimentary remnants preserved from these episodes that you can define this history with confidence. I could talk about Brazil, but I don't really have time. Briefly talking about West Greenland, the thing about Brazil and West Greenland is that we've got these marine horizons at up to 1 kilometre or more above sea level today, and they're post-breakup marine horizons. So even if you don't accept the after or the low temperature thermochronology, this is hard geological evidence that after breakup this area subsided, marine horizons were deposited, and then after breakup they've been uplifted to 1,200 metres above sea level. In fact, when we look at the after and VR and everything else in here, we find that there's been another kilometre or so removed off there, and that began at about 35 MA, removal of that sediment. And 35 MA is a popular time for this sort of movement around the North Atlantic and Arctic. Here, these green dots here show areas where we've seen the same sort of exhumation beginning at 35 MA from Alaska, the Mackenzie Valley, West and East Greenland, up into Svalbard and the Barents Sea, and in the UK. We also see other events in the North Atlantic at similar times. 60 MA is a good time for things happening, and then there's a number of different episodes in the Neogene. So we're not saying, of course, I just want to emphasise, we're not saying this whole area was exhumed at that time, but what we're seeing is that we see evidence for exhumation at about 35 MA in all these locations. There are obviously areas that weren't exhumed at that time. But 35 MA seems to fit in with a fairly drastic plate reorganisation in the North Atlantic, and this is from Carmen Geiner et al. Recent paper. So this is really what brings me here today, to suggest that these events that we're seeing are somehow related to plate motions and plate reorganisations, and there's something plate tectonics seems to be playing a role. That was the northern hemisphere. Moving to the southern hemisphere, we see a similar sort of synchronicity in events, particularly in the late Cretaceous, in the Campanian through here. We see exhumation in South Africa, Namibia, Angola, Equatorial Guinea, northeastern Brazil, and we also see a number of Cenozoic phases, and these seem to tie in with phases of Andean orogeny, and that's from Peter Cobbold's work here, these three phases. We also see other events in the mid-Cretaceous, early Cretaceous, and Jurassic that are more or less synchronous. So we're seeing exhumation happening at the same time across a wide area. If I remember to put this slide up again, these are areas that are showing exhumation at about 80 MA. And that again, very broadly at least, seems to tie in with some sort of plate reorganisation in the Atlantic here and in the Indian Ocean here at about 75, 80. This event we tie to about between 75 and 80 MA. So here we are talking about this. We've been doing this sort of work for 30 years and telling people about it. And you might ask, why are these movements not more widely recognised? Well, one reason is that up to very recently, the presence of these sedimentary remnants hasn't been taken into account in any thermochronology studies. And one example here in this study of East Greenland, published by another group, came up with these continuous exhumation histories from the Paleozoic to the present day. But in this area, we have Carboniferous and Jurassic rocks preserved at the surface and sedimentary remnants here and here and here. And if we include those in the history, again, you turn the continuous cooling into time, you integrate into that history times where these rocks are very close to the surface. And you end up again with an exhumation, burial, exhumation, and so on. So there's a large number of early thermochronology studies in particular where those sedimentary remnants on basement were simply ignored. And the second reason is that for a long time geomorphologists looked at these old surfaces preserved, and we saw some beautiful peneplains yesterday that had been uplifted to 3 kilometres or more in Simpson's talk. Right, high five. And this is typified by the classic idea of the evolution of continental margins, where you have a high plateau and an escarpment coming down to a coastal plain. For many years, these high plateaus at continental margins were regarded as stable, long-term plains that hadn't undergone really much of anything. But looking at the AFTA data and VR data and other things, in South Africa here, this is a north-south cross-section through Beaufort West, north-south, and here's the present-day topography and the escarpment here, but this is based on the work of Justin Tinker et al. In 2008. Their results suggest that that area was buried by 2 kilometres of sediment in the late Cretaceous. So it's very difficult to see these things as these surfaces as being long-lived, stable surfaces. Now, this gets me on to my favourite hobby horse about talking about missing section, because this has long been a very great source of controversy. And recognising these events that I'm talking about relies heavily on missing section. And up until very recently, one of the few books that ever took this question seriously is this book by Derek Ager, The Nature of the Stratigraphic Record, which some of you might know. In this book, Ager commented that what looks like a continuous section here is actually a whole series of gaps interspersed with a few periods of deposition and preservation. So you only see a small fraction of what was deposited, and the rest of the history is represented by gaps. In fact, if we put our slant on that, what we invariably find is that these gaps in the section represent times when a huge amount of section was deposited, huge being open to interpretation, I guess. A significant amount of section was deposited and then removed, as I've been showing you here. And this is much more typical of what we see in our results. And this has caused a whole lot of controversy in different places here that's still ongoing, and some people still refuse to believe, for example, that the Sydney Basin has ever been more deeply buried than it has been. So, from our point of view, Derek Ager said that the gaps were as important as the record, but we would say that the missing section is just as important as the preserved section, from our point of view. And this brings us on to mechanisms. How long?
2 minutes.
Good.
2 minutes to 15. That's 13.
Yes, thank you. Just briefly on mechanisms, as I said, we don't know what's causing these events. Mantle convection and dynamic topography has been suggested by a lot of people, but I'm not sure that it can do this repeated burial and exhumation, which seem to come as a pair in all these studies. Interplate compression has been suggested, and there are others which there's no point going through because none of them actually fit what we see. So we need something else that's consistent with these observations, and there is a lot of data that can be used to calibrate such mechanisms. And just finally, last slide, why are these important? Well, they're important because if you don't take them into account, you end up with the impression of slow, continuous processes happening over hundreds of millions of years. But what this shows is that things are actually happening much more rapidly on a much more shorter time scale. So to get a full understanding, you need to take this into account. On a more practical level, leading into later talks, burial and exhumation of this sort controls the hydrocarbon prospectivity in many parts of the world, like the Barents Sea, North Africa, and the UK southern North Sea, just as three. And finally, if we do understand these processes, then we might learn something new about plate tectonics. Thank you.
Well, I can say Lydia was first out of the traps this time as the lights came up.
Paul, as you say, you've been noticing these events for over 30 years, and you tantalisingly say we don't have a mechanism. You must have some views. So are you prepared to share those views? He sighs.
I really don't have a firm idea. It goes back to something Nikki said yesterday or the day before about the mantle being bouncy. And to me, this just shows it's even more bouncier than we thought. But it could be any one of those things. Mantle circulation obviously springs to mind. Intraplate compression is a possibility, but I'm not placed to do that sort of work to test these models. So we need people with that capability to take on this mantle and try and explain what's going on.
Okay. I think there might have been more than one question, but we'll take one for now. Could you just hold them, because we will come back. I mean, I've had a few conversations with Paul over the last couple of days. This topic of the mechanism that Lydia brought straight up is quite important, I think. And
that's why I'm here.
It might be something we can return to in the last 10 minutes or so. Anyway, Cindy, yes.
Is there evidence then are there deltaic sequences offshore, large, you remove those large amounts of material in pulses, then the stratigraphic record needs to preserve that. And can you also, is there indications of the updip extent of these erosional episodes in the crustal thickness variations? Removing 3 kilometers is detectable, certainly, with many methods.
Well, this is one of the problems that we face, because it's not just erosion of 3 kilometres, but it's deposition as well. So you end up with very low angle processes. So there is no up dip, really. It's happening on a very large scale, low angle situation. So it's very difficult to do that.
Okay, but we'll move on now, but I would say don't go away, Paul, because you might be coming back later.
I'll go to Mr.
Okay, our next speaker is Teunis Heyn from BP America. Sticking on the theme of sedimentary basins, Tony's going to take us to the Gulf of Mexico.
Yes, good morning. I'm originally from Holland, but I moved to the United States when I was a young man, so I have an American accent. These are my co-authors, Mark Hogarth from Cambridge, and the rest of the crowd there they're all VP people from the Houston office. I'd like to dedicate this to Jack Bird, who recently passed away, and he was my thesis advisor at Cornell University. This is a picture of the Colorado Plateau. It's come up pretty dramatically in the recent past. And I like to draw the linkages between this sort of uplift to the kinds of things that we see in the Gulf of Mexico. So the first thing I'll do is I'll start with a section, and it shows two restorations. The top one's actually Middle Miocene, the middle one Oligocene, and the lower one is a Middle Eocene. And what you see on these sections is a very large gravity slides system with extension up dip and contraction down dip. So this is what things look like during the Middle Eocene. Then during the Oligocene, what you see is a second gravity slide system that's set up simultaneous on the top of one that's active at a deeper level. And then in the more recent past, what you see in the Middle Miocene is you see a gravity system that sets up and it cuts through this system and then creates this fold belt that we call the Perdido fold belt. Now, I frequently deal with people, and the common assertion that people will say is that the sediment input into the GOM and thermal subsidence have caused this type of gravity sliding. And I think there's a lot more going on, and I'd like to draw the linkage of what's going on to plate tectonics. So this is a map. What I've done is I've put the sort of observations on a map that Jim Pindell and I worked on at BP some time ago. And here you see the lower tertiary gravity slide, and that's the line location that you see right there. On this map, what you see is the plate boundary here with the North America. This is North America here, and this is the Caribbean plate and the Pacific plate. And at that time, you had very simple subduction with the Farallon plate going underneath there. And you had an orogenic belt with folding and thrusting here and some foreland basins that sit in here. And you had a peripheral bulge in these blue lines that you see right here. Also, what's happening at that time, based on the seismic that we have onshore, is you had a lot of basement inversions in this part of North America right there. You see a great big thick in here. These are contours. I've sort of simplified it, but what I'm showing here is a thick where this overall extensional thick is. And then when you go further outboard, actually further out in this location, you see a second thick. And we'll talk a bit more about what that might be later on. So the extension has been very well documented in the literature. This is from the Diegler paper. And it's very, very well documented. There's not really a lot of controversy about that. And you see the expansion of this section associated with the extension in the up dip of the gravity slide. What might be a little bit more controversial is the folding down dip, which is really, these fold axes are really based on isopac thickness variations. So where you have a thin, you just draw in the anticlinal fold axis. Where you have the thicks, you have the synclines. And a lot of the contractions actually accommodated by salt squeezing out of the system into canopies that are sitting higher up in the section as well. Okay, now let's move on to I'm going to skip the Oligocene gravity slide because there's not a whole lot of time in this presentation, so I'm going to go right to the Neogene gravity slides. And you have one in the northern part of the Gulf of Mexico, and you have another one in the southern Gulf of Mexico. So this shows the line locations in the black right there. In terms of plate tectonic setting, what's happened is a triple junction has migrated along the edge of North America as North America moved westward over top of the western side of the Farallon plate. So the plate that's called Cocos is really the remnant of the Farallon plate. And I'll show later that we might be able to identify the edge of the downgoing subducting Farallon plate underneath the Gulf of Mexico on the basis of tomographic information. The important thing here is, in this diagram here, is you still have sort of Laramide style contraction going on here, uplift associated with simple convergence along plate margin. And in this part of the world, we've overridden now the upwelling, the mantle upwelling region. And you see a massive region of uplift and basin and ridge extension in that part of the world. So what's really interesting is that this slide that you see here, this slide, and the continuation of it here, they're sliding in that direction. Over here, that slide is going northward. You see it's going northward. And you see the thicks in the middle Miocene sit out here, and then there's a second thick here. That's this one right about in there. So these things are actually going in opposite directions, sliding towards the middle of the Gulf of Mexico. So what I did here was I took a grid of seismic line here. And basically what you can do is you can see whether the horizons are truncated by erosion. And I just mapped those up into the air. And then I created an isopack map between the present day surface and those projected horizons. And then I calibrated that to vitrinite reflectance, and you can come up with a map in this region right here that shows uplift. And you can see there's about 6,000 feet of uplift. It's associated with this larger, broader Colorado Plateau region. So if you restore that back to, let's say, early Miocene, this particular line, you see that all of this section's actually been eroded. All this section that was here has been eroded, and now it's been being redeposited into the deep water Gulf of Mexico. So the way I actually view this isopack here, it's the cumulative uplift of both laramide type of basement inversion as well as this neogene uplift. This is a map by Gareth Roberts, where the Cambridge crowd and Gareth analyzed the streams in this particular region, and they were able to determine the cumulative amount of uplift in this part of North America. And you can see, how much it actually they calculated up to 3 kilometers of cumulative uplift. You see also the gravity anomaly of the free air, the long wavelength free air, which is quite a good proxy for uplift and subsidence. And here in the GOM, what you see is a negative, which suggests subsidence. This is a beautiful diagram that Gareth put together. I can't really improve on this at all. I totally agree with all this stuff that he's depicting, but he basically sees 2 pulses of uplift based on his drainage analysis of the rivers. One during the Neogene and one during the lower tertiary. Also, he points out that and Galloway shows 2 massive pulses of sediment entering into the GOM. The diagram has a lot more things on it that supports this interpretation, but we don't really have time at this point to go through all of that. The other observation by Galloway is that the early river systems in the Gulf of Mexico sit in the west. And then later on, as you progress into the Neogene, everything shifts to the east, which suggests massive amounts of uplift pushing the rivers towards the east. Now, Mark Hogarth and Nikki White and the Cambridge group did this work, and they identified an area of residual topography, negative residual topography in the western Gulf of Mexico. There's a very, very large area of negative residual topography. So if I just stick the gravity slides on there, this one goes in that direction, that one goes in that direction, suggesting what's going on in this part. Is it the Farallon plate that's drawing this part of the Gulf of Mexico down? So I was reminded by Nikki and questions yesterday in the audience as well that this area of blue, it's an interpretation that we make that it's the Farallon plate. It is not fact, right? So, but what we've done here, this is an east-west line through the GOM. So this is the coast of Mexico, the onshore basin and range province in onshore Mexico. Here is the negative free air anomaly over the Gulf of Mexico, and what you see is this negative area of fast velocities, which can be interpreted as the downgoing Farallon plate. Okay. So this line that I just showed you, this is the free air gravity map right here, and so you can actually map the edge of what we think might be the Farallon plate sitting right there, where you have that negative residual topography right there. Now we can take a look at a line that goes through the southern part here across the plate boundary. What you see on topography is you see the present-day Cocos plate, which was once attached to the backside of the Farallon plate. So here's the Cocos, here's that subduction zone, right? And so that's broken off from the back right there. You can see that as well. So what we think is going on here is that this is just going up because it's bumping along the base of the Yucatan block right here. So that's coming up where the area blue is. And then you have the drawdown region in the middle. That's giving you the gravitational potential for this gravity slide. The orogenic belt fabric is this one, but that's the gravity slide that's present there, and it's at 90 degrees to the orogenic belt that you see there. So sort of as a summary diagram, kind of illustrates the overall tilting of the basin. This is the line that comes through here, the two maps that I've shown you. You see the early geometry and then the later geometry right there. And the idea is Farallon plate's going down, your depot center sits approximately across there. You get a drawdown subsidence in here. You have a peripheral bulge in a foreland basin. Gray's analysis of the onshore area here takes off about 2 kilometers during the Neogene. There comes the Neogene uplift event as the triple junction migrates down like this. This pops up because of mantle upwelling. It tilts the basin, pushes the rivers over. You get the sediment over here. And then the Farallon sits approximately in that position. At a sort of super broad scale, this is sort of the Tanya Atwater story from many years ago of, driving the triple junction south. The question still for me remains is the location of the thicks that we see. Does it directly sit on top of that downgoing plate? Or is it just also influenced more by where the rivers are bringing in the sediments? So there are the conclusions. I think you can probably read those. I'm right out of time. So there you go. Oh, I'd like to also...
Tony hasn't run out of time because we've got a couple of minutes for discussion, I'm pleased to say.
I'd like to thank Nikki and Jim in particular for pushing me along with some of this thinking. And then there's some of the other people that have really helped me out in my BP career.
Okay, I've got, I can think 2 questions straight away. So, Jim?
Jim Chalmers, Geos Copenhagen. If you've got a downgoing slab going in underneath Gulf of Mexico, surely you should be getting volcanism there. And if not, why not?
There is actually volcanism. The Mexican ridges is actually going over top of a pluton that's intruded into the sedimentary section there. But the volcanism is really restricted to 100 kilometers above the downgoing slab, right? So that's where the ark's actually sitting about 100 kilometers above the downgoing slab. So the slab that I'm depicting is deeper than 100 kilometers.
Mike Reid. Firstly, a reminiscence and then a question, if I may. Another BP geologist, whose name would be very well known to many people here, was Bob Stoneley. And Bob and I were working in New Zealand together back in the days before plate tectonics, in the early 60s. And Bob mapped a really very remarkable series of gravity slides which had come from the northern Raukumara Peninsula of northeast New Zealand and had slid southwards in the around about mid-Cenozoic times. Later on, I was working a little bit further east in largely upper Cenozoic sediments, and I saw exactly the same kind of thing, again sliding from the north of the Raucumara Peninsula, sliding southwards, giving mud volcanoes, mud diapirs, and so on. So that's my reminiscence. The question I have is, what do you think was the angle of the surface down which these slides took place, presumably lubricated by overpressures?
It's only like a degree, not very much. In fact, for the early one, it's not a gravity slide; it's actually gravity spreading. So where the basal detachment, you have a deep, slippery shale unit, and the basal detachment actually dips back towards the continent, and it's the tilting of the basin. The detachment is still dipping back towards the continent. And it's just it's kind of like a glacier in many ways. It's the loading of the sediment, but in combination with the tilting. But it's a gravitational slipping that's going on. So it can actually dipping back into the continent. So it can be from 1 degree back into the continent to tilted 1 degree back out into the basin.
I think we should move on, but I can see there are some more questions. So can you hold them for a few minutes, and we'll have time to come back to them. Thank you very much, Tony. Right, our final talk in the session is by Max Dobson. Max is going to take us northwards from the Gulf of Mexico up to the Aleutian Trench.
Thank you, Chairman. Well, this is the first opportunity you've had for a talk which is going to effectively destroy many of the plate components that we've been talking about and recycle them. You'll notice up here, when I'm talking about the Aleutian Trench, the one thing that's missing, particularly in the allocyclic section, is sea level change. It has minimal effect in this particular cycle. So I'm taking plate tectonic elements, mostly, of course, island arcs, and I'm going to destroy them, recycle them, and put them back, effectively, into various types of accretionary prisms. You will all know the area that I'm talking about. This is the area of Alaska, and here, and the Yukon, and here, indeed, are the typical type of what we might call large glaciers, which bring vast quantities of material, shall we say rock flour, down to the coast. All this work really started with Dave Scholes, and I was a member of his team, and when we were doing the EZ, or perhaps I should say EZ for some people, and this is the latest sediment interpretation. Now, these are the primary elements that we need to look at. First of all, of course, you've got this very large transform fault, and we have also, of course, the Yakutat terrain here. This is left California, mostly in the tertiary. It is mostly tertiary material, and it's got jammed here in this corner of the Gulf. There is some elements here suggesting there may be some subduction going on. So we have these Mount Elias mountains here, of which you've just seen a picture. But over on this side here, we've got the Chugach Mountains, another 4-kilometer range in terms of height, and behind that, the Alaskan range. So there's a vast area here which is being eroded by glaciers. And there have been glaciers up here for at least 4 million years, as far as we understand. Now, the other elements, of course, is the trench, which I shall now concentrate on in a minute, but also the Kodiak Bowie seamounts, and again, the Patton seamounts here. These play, curiously, a very important role in terms of looking at the sediment that is accumulating here in the trench. It creates a series of compartments of changing characters in terms of the sediment. If we look to the north, you can see these primary elements here, and these are a series here of old island arcs, of which there are at least 3. Most of them of tertiary and late Cretaceous age, so there's quite a range, and there is the Alaskan range material. And here we have part of what is now known as the Chugach Mountains. We can look at it in a slightly different way. The Wrangell composite terrain, as you can see here. And behind that, of course, we've got a large number of intrusions as well into that series. So all this material now is ripe for removal. And that's, in fact, what the glaciers have been doing for many millions of years. But I'll concentrate over on perhaps the last 1 million years or so. If we go to the far west end of the arc, the situation is very different. Yes, we've got all these islands, and you can see them here quite happily, and they get smaller and more indistinct. One of the reasons for this, of course, is that we're looking at two situations. The old cooler plate, and its vector is there, as you can see, almost north. I'm delighted to hear, in fact, earlier, I think perhaps a day or two ago, that the Emperor Seamount chain and its relationship to the cooler plate still exists. So that particular vector, as you can see there, essentially north-south. Now, the cooler plate, of course, died out 43 million years ago, according to Dave Scholz and his colleagues, and then was taken over in terms of power movement by the Pacific plate, and those are the vectors there. And the first thing you'll notice straight away is that when the Pacific plate subduction has taken place, we get this kind of parallelism here in this section of the old arc of the cooler plate. That is going to play a significant role in terms of trying to decide how the changes have occurred with the actual trench material. So that's just a resume of what's been going on in terms of that Aleutian arc end in the cooler section. What I'm really looking at now is how all this sediment is moving. You can see straight away that this is the present situation. The first thing to notice, of course, is if you take the Chugach fan here, there are abandoned channels. A rough calculation between the two channels, this one which is active now and the earlier one, it suggests at least 100,000, but more likely 200,000 years. So, in point of fact, the main source of the sediment is from here, but of course the plate moves on. And so, of course, we've got a series of shinglings here on a large scale. The other thing to bear in mind here, which is very unusual, and you'll see this in the trench, is that if you look at the Surveyor channel here, and look at the length of it relative to the scale, you'll notice it's more than 500 kilometers long. This is an extremely long and uniform channel, low sinuosity, very strange, and it may well be, and I can't answer for this, but it may well be that this plate here, the Pacific plate, of course is warm relative to the cooler plate further west, which is old and cold. So it may well be that there's a slope. We need a slope here approaching 1 degree or maybe even more, but certainly that is necessary in order to carry this material down and eventually into the trench. Notice that much of that trench at that end has been bypassed. The other thing about the Chugach fan, we'll leave these fans really because they don't really play a role in this particular presentation. One of the things about the Chugach fan here is you see it goes, and like all the others, it has to negotiate the seamount chain here, and it has done that and ends up with this series of end fans here on a very large scale. Look at those fans. They are enormous, 75 kilometers long. There are 7 of them here, and they're more than 50 meters thick in each case, and they're shingling. The point I want to make about this area, though, is this huge area here will contain at depth under the present surface, a large number of earlier channels, a large number of those very large fans, all moving towards the trench to be accumulated there. So we'll leave these alone. Here are the seamounts. As you can see, they're extremely large. They used to be, they used to all have feminine names, but the United States Geological Survey prevented marine geologists from naming them after their girlfriends. So now we've got all these rather curiously ordinary names. Now here we are then, and we're going to look at 6. We're going to have a look at 6 examples down the trench here. The first one is, you can see that the glaciers go straight to the trough end, as it were, there by this transition fault here, and this is all part of the Yakutak terrain, and go straight down. And almost immediately, we have a well-defined channel. There are the sediments coming from the north. At the present time, the glaciers feed into the Copper River and the Sistina River, and that material will be coming into the trench across here. At the moment, as you can see, there is supply from the Bering Glacier and the Malspina Glacier and so on. So there's a lot of supply coming in, as well as from a direct source here. As we go around the Kirov corner here, you can see again that there's a well-defined channel, and of course, the first of one of these very large debris slump systems and sequences there, extending across quite a narrow accretionary prism. Now, I'll have to move on fairly quickly, but you'll see there it is again. That's it up there, and there are several others. In fact, there's vast quantities of sediment coming in from the north, from the Chugach Mountains. What does it look like? Well, fortunately, the DSDP 180 is right in there, and we can look at that in terms of their interpretation of this sequence. The other thing we can look at is that as this channel carries vast quantities of rock flour, there are cases where there are depressions in the downgoing plate, and it's at that time, of course, that we get not only levees, but really what we might call crevasse splays, and here they are, very large. They're 10 kilometers or more. These are enormous discharges here in this part of the trench. So, oh my goodness me, I can't believe you move. And there is the example. There is the example of 180, and you can see we're looking at about 150 meters of sediment, and they have also recognized, of course, the interglacial period, so they can date this 700,000 years of material there quite happily. So we have a control on that sequence, and as you move further on, you can see where the surveyor channel comes in. This surveyor channel brings an enormous amount of material. This is a large sand fan here. This is an earlier surveyor channel, and it's now re-establishing the actual large channel down the actual trench itself. The thing to bear in mind is this is where the seamount chain impinges actually on the trench. It's occluding it, and of course it is destroying the old accretionary prism. This is the first way in which you can see the sections are being compartments are being created. And that is the section there. You can see the old channel. This is slumping. There's the old channel again. And here's the trench fill. There's the surveyor channel. And it's actually backfilling the trench at this point with these huge levee systems. If you go further on, here is the next occlusion. And this is the next seamount chain. This is the pattern here. And the same situation is applied here. And you can have a look at an air gun section of that, and you can see this, here is the pattern here, and here is, in fact, the actual trench, and there is, again, the channel. All right, can I keep going for another half an hour? So when we get further along, the situation changes dramatically. There's no more channel. And what's happening, of course, is that we're beginning to see the whole lot now being affected by oblique subduction. This oblique subduction is destroying the trench. It is also affecting the accretionary prism. I will avoid the next one and say to you, as we go even further west, as you can see here, the obliquity has increased dramatically, and now we get just destruction of that arc, the old cooler arc. You can see there the block rotation on a very large scale, producing these summit basins, and indeed you see these sliver basins here, where sediment, which is being eroded from those remnant islands, there's no volcanic activity there. In fact, there's only 4 volcanoes active in the area up towards the Kodiak Island. And here, of course, are the shears, which are helping to destroy everything. And if you go further west still, here is a situation where the sedimentation patterns change in each case. If you go further west, it looks like an incipient transformed fault. That would be the general model for the eastern end of the trench. All the elements are there, all the characteristics of which you are familiar, and particularly, of course, with these very dramatic channels and their huge overbanking in terms of levees. If you go right in the far west end, here is a rather primitive cartoon from the Sonde cruise in 2012, where they dredged the whole of this section here, where the Stalemate Ridge, part of the old aseismic ridge of the cooler plate, is being fractured here. And all they dredged up, of course, was siliceous peridotites, melange, and melange here as well. So there may be some abduction going on. And there is confirmation that there are large breccias here on this, this old ridge, really. Now, we call it the Aleutian Ridge, but it's the remnant, as it were. And so that is the cycle pattern, certainly in the east. The situation in the west, in terms of the arc, of course, is vastly different. And so you can create 5 zones on this arc in terms of the sediments, the sediment recycling, the destruction of the plates, and the reintroduction into the trench. Thank you very much.
Thank you very much, Max. Well, we'll move straight to questions on Max's talk. Can we put the lights up? No. Lydia.
I'm so sorry, but I just want to, I'm sorry to ask yet another question, but I found that absolutely fascinating. In particular, I'm very interested in the pattern of all those channels and their shingling, as you pointed out, in the seabed. Now, I've missed all of this, so presumably it's published somewhere? I mean, when we get access to the data?
The Geological Society of London.
Oh, dearie me. That makes me feel even more embarrassed. Anyway, I'll chase it up with you later, but that whole pattern of the things moving and what the fans are doing in the levees is fascinating.
Any more?
David Shilston. I'm fascinated by these very long channels, 500 kilometres, London to Glasgow length. Are these pulses of turbidites moving all the way down in a single episode, or do they move in parts? The gradients are so slight.
I can't answer that. I don't know that. We don't have that information available. But yes, I would be interested to know whether, in fact, the idea of this slope, perhaps a 1-degree slope over 1,000 kilometres or so, is achievable in terms of warm plate, cool plate, and whether that is the driving factor in this case. Thank you very much.
Rob, did you want to say something?
Yeah, I mean, the interesting thing is as you change the shape of your basin, as you close trenches off and impinge bits of seamount onto there, you'll change the level of confinement for the turbidity current. So you'd expect, before you switch it off, as you go into confined flows, you'd expect to see a period of bypass and the system to jump way down system. Do you have the resolution to see that? Okay.
Sorry.
Tony.
A couple of questions sort of buried in one, and whether you see the effects of the Aleutian outer rise, the flectoral bulge, in controlling some of the direction of the channels, and secondly, whether these channels, some of the channels are reusing their own paths, as it were, sort of some kind of aquaplaning on the existing slides.
Yes. With reference to the outer trench high, when you have a look at particularly the seamount chains, normally if the seamounts are relatively small, they will be sliced, diced, and have no impact when they reach the trench. Yes, it appears that they do prevent some of these channels extending to the trench, and that is why, particularly the Surveyor channel, it goes for more than 500 meters before it actually is able to get into the trench. And it's only at that particular point where it does cut into the trench that the outer trench high has been very efficient in slicing up parts of the ocean floor.
Thank you. Well, we've got just over... Lydia wants to come back on one again.
We've been looking at the behaviour of channels in the Niger Delta, and again, they don't go for anything like the long lengths that you say, but they're going from the slope right down to the sort of the outer slope, so from the shelf to the outer slope. And we've been measuring the rates at which structures are deforming, so it's not quite the same thing as what you're saying, but tiny, tiny rates are enough to affect what the channels are doing. And even at times when we can't detect tectonically the rates, they're still affecting what channels do. So very, very subtle seabed topography. And I'm talking about strain rates of less than 0.5 millimeters per million years. So very, very low rates. I have the numbers. So that bears some relationship to those questions.
Thank you. Right, well, we've got 5 or so minutes to the coffee break. I'm aware that I could tail discussion on one or two of the other papers, and I know there was a question on Paul Green's talk. So, Paul, where's Paul?
Chris Mark, Trinity College Dublin. Paul, just to talk about some of your presentation there, I think some of this reactivation in continental interiors has got to be quite strongly partitioned. And there's a lovely example in Northern Ireland where you find the Antrim basalts and the Mourne granite within 15 kilometres of each other. They're pretty much overlapping in age, Paleogene, and yet one, of course, is a surface feature and the other ones come up from at least 1 or 2 kilometres depth. So you've got exhumation there on kilometre scale, but it's been very strongly partitioned, probably onto old structures. And I suspect that may be the case in some of these other areas as well. And I'd just like to bring that back to Dixon Cunningham's talk yesterday, where he was presenting deformation and reactivation of basement structures in continental interiors, and asked the question, how do you recognise those in the rock record once they've been eroded away? And I suspect this is our answer.
Well, that's right. I mean, in terms... don't really know what to say about the Northern Ireland example. Can't really add much to that. But in terms of spotting these events in continental interiors, the only way you can detect them is to see the effects of what was there and has now been removed. And Dixon's lucky that he's got the tectonically active area and he can see these things happening. But in older terrains, the evidence is obliterated.
Thanks. And in support of, or in reference to Cindy's question, the Nile Delta turns on quite abruptly offshore. It's at some time at the top of the Oligocene. The Congo fan is basically built out on a starved basin, a thing called the Irapi, which is the source rock in Angola in the Tertiary, and that's dated from Cretaceous to the end of the Paleogene. And they're very similar situations whereby the response internally in the continent of Africa seems to say that something's happening at 20 million years or 22 million years. And it's what Cindy's been working on for most of her life, I think.
Just to add to that, I think in terms of what Cindy was asking about in terms of tracing was it Cindy or Lydia that said that, about looking at basically doing the source sink calculations and looking where the erosional detritus goes. I think you need to take a very wide view, and we're not dealing with local effects where you have uplifted dumping sediment there. We're dealing with huge regions that are eroded, and that sediment can go a long way, and then it might be eroded again from where it ends up. So you get these multiple cycles. So
Rob, can you go to the back, please?
The whole concept of source sink is very difficult unless you can identify your source and you sink properly.
Yeah. I have another question for Paul Green. Mike Simmons from Halliburton. First of all, to support what Mike Daly's just said, yes, those of us who work in the petroleum industry do see major sediment influxes at around 35 MA and 110 MA. But my question really is, when you say there's an interregional exhumation event at 35 MA, what do you precisely mean by that? Because exhumation isn't instantaneous. So what is the rate of exhumation, the duration of the exhumation period?
That's a very good question, and it's one we really can't answer. And I try to be as vague as possible whenever I quote these things, because we just don't have the control on the rates. What we can tell using these methods is when it begins. more or less. And so we tend to put a little squiggle in front of the 35 MA and say it starts about 35 MA. Our techniques aren't what you'd call high precision, but they're giving you information that you can't get any other way. So, you know, the rates is one thing that's very, very difficult to see.
I'm aware the clock is ticking, and also that I curtailed discussion on Teunis Heyn's paper. So before I throw it back, I can see Jonathan wants to ask a question, but is there anybody who wanted to ask Tony a question who wants to come back with it at the moment?
Yeah, Dixon Cunningham. I was wondering about the Llano uplift, the Ozark basement uplift, St. Francis uplift, and if that was related to the Farallon, in the wake of the Farallon descent at great depth, if that would be tied into that.
So the Ozarks are clearly uplifted in the Neogene. It's a very recent uplift. There are several of the basement structures like the Llano, the Monroe, some of these basement arches that have actually Cretaceous pulses of uplift. Then there are Eocene pulses of uplift. And then you have the really broad Neogene uplift superimposed on those. So the Neogene uplift is this really massive, broad uplift, whereas the older uplifts are more associated with distinct basement blocks.
Okay, so I think Paul wants to comment on that as well.
I agree with that those uplifts have had a multi-stage exhumation history. And the thing to bear in mind is that the most recent event is much more easy to see than the previous ones. And so you see the big Neogene uplift in the Ozarks and so on, but there are bigger events, well, big events also in the past there as well.
Okay, Jonathan wanted to ask a question, and I didn't let him a couple of minutes ago. Just to...
Well, it's curtailing the discussion with Paul Green. Is that okay, or do you want to keep the green discussion going?
Well, carry on, Jonathan. Ask who to.
Okay, well, I'm in danger of sounding like a dog with a bone here, but I got a question for Nick again, and really turning the same question that I asked earlier around: is it realistic to have friction coefficients of 0.1 to 0.2? I realise that some fault rocks and cataclasites can have those kind of low friction coefficients, but that's kind of a circular argument, in that you require a lot of shear in order to generate those fault rocks. You know, I would assert that, for example, you barely ever see a fault and outcrop that isn't associated with synkinematic mineralised fracture systems, i.e. fluids.
Yes, of course, we're being dreadfully dishonest, aren't we, really? One way to get around it is you assume that the thrust faults do the job of reducing the friction coefficients along at least parts of what become the low-angle normal faults. So at least a contingent of people think that severe desert attachment follows the Pavant thrust. So you whack down the friction coefficients initially by the thrusting, and then you reuse it. It's still an embarrassment because there are still chunks of the detachment which were not faults originally, and you still have to get it down to 0.13 to make it move 11 degrees. And in our manuscript, we make noises about things which could help, like there is Jurassic salt in the subsurface, and there's Oligocene salt in the basin. So we make noises about that. The alternative interpretation is that there is no fault there at all. And what we're doing here is we're simply saying, okay, if we simply run with a mindset that is the current North American mindset, that's what's implied, so that it's testable. If you drill a hole, that's what you're going to find. But it's just as likely when you get down to 2.8 kilometers, you find there's no fault there at all.
Okay, I've been given the go-ahead by Rob to keep going into coffee. I hope that's for a short while. I hope that's okay. So, Nicky.
Nicky White from Bullard Labs. A comment on Nick Christie-Blick's and Paul Green's talks, where I completely agree with you about the comment about sea level, apropos of which last year I heard Bilal Hack give a talk about the Hack curve, where he said it's all completely wrong.
Brilliant, absolutely brilliant. Yeah.
So the issue then, with respect to both your talks, is there's increasing evidence for quite rapid up and down movements around the world, and things in the stratigraphic record that don't look like global used to see, but may be to do with things in the mantle. Apropos of which, it's worth remembering examples like in the North Atlantic, there's quite good indirect evidence that the flow rates associated with the ice and plume as the material moves out pancake-like sideways, the flow rates are more than 10 times plate velocities, so up to 500 millimeters a year, within probably a fairly thin channel, a thinnest channel immediately beneath the plate, within which you can get small temperature anomalies. You don't need very large temperature anomalies within this thin asthenospheric layer to generate significant amounts of transient vertical motion. And there's excellent evidence for buried ephemeral landscapes on 3D seismic around the North Atlantic that may be something to do with this sort of phenomenon. So making things bouncy is probably not terribly difficult from a convective point of view. I think the real key is getting better observational constraints on both of the sort of things you guys talked about.
Yeah, I'm very sympathetic with the view that there are a lot of mechanisms at different time scales and length scales, and that the trick is being able to tease them apart. That's not so easy. And I'm also sympathetic with Ken Miller's view that there's now a pretty good, at least for the younger records, the Neogene record, at a well-behaved, relatively well-behaved passive margin, it's not perfect, that there is a pretty good correspondence between that and the oxygen isotope record. So you know you've got a signal which relates to the southern hemisphere ice sheet. It's simply not the only thing that's going on. And it's small, yeah.
Okay, well, thank you very much, everyone. I think we'd like to wrap it up there and go to coffee. I'd just like to thank all 5 speakers for keeping to time.